When we say worst case, we often pull the scariest clip from the last movie we watched. That's natural, but not helpful. In real watching, worst case means the most harmful thing that could happen under the laws of physics and still be remotely plausible. To keep this honest, we use 3 simple rules. First, we only count events the sky can actually deliver with an object like this. If the scenario needs magic, it doesn't make the list. Second, we talk about probability, not just possibility. Could is a wide word. Likely is the one that helps you sleep. Third, we define harm the way emergency managers do. Real outcomes for people on the ground power systems. Water, health not. Viral headlines. So, what is on the table? 3 broad buckets. 1. No direct effect on Earth, at all by far the most likely. 2. Minor indirect effects in space, short-lived upticks in dust or small debris that engineers already plan for. 3. A direct impact, very rare event, with very small odds in this specific case, but still worth explaining so you understand why the odds are small. If you can see those buckets clearly, the noise drops away. Most nights, the sky lives in bucket 1. Occasionally, satellites care about bucket 2. Bucket 3 is the place we plan for, test for, and almost never visit. To make this practical, think of driving. The worst case isn't a meteor falls on the car. You don't plan for that. The worst case is black ice ahead, because it's rare but real, and we know how to avoid it. Slow down, keep distance, look for shine on the road. Space has the same feel. We're not planning for a wild card. We're talking about the kind of risk that shows up in data first and gives you time to act before it matters, if it ever does. Interstellar objects don't orbit the sun like planets and most comets. They pass through. In simple words, they're moving too fast to get captured. Astronomers measured that with a number called eccentricity. If it's less than 1, the path is a closed loop. If it's greater than 1, the path is opener. 3-1 ATLAS, like Oumuamua and Borisov before it, is on an open path. That fact alone knocks down many scary ideas. A body on a one-time pass doesn't hang around to pull on planets or wait for a turn at Earth. It comes. It goes, we watch, we learn, and it fades into the dark again. Speed is the other big word. A fast traveler spends very little time near any one world. That short window matters. If you ever hear unlikely impact, you can translate it to geometry doesn't line up. Space is mostly empty, and even a small miss near the sun is millions of miles. For a real collision, the math would scream early and loudly across public pages, the Minor Planet Center, the JPL Small Body Database, observatory feeds. You wouldn't need a rumor to tell you. The numbers would. And because this object is not bound, even a dramatic breakup near the sun would turn into smaller pieces on similar open paths. Not a storm that homes in on a planet like a homing pigeon. There is another quiet comfort in an open path. Gravity helps you even when it isn't trying to. Any small deflection from outgassing or a weak jet tends to change the timing and distance more than it changes the aim at Earth. The upshot in real life. Interstellar mostly means beautiful and brief. If you remember that, you have already freed yourself from the loudest myths every time a new comet is in the news. Someone says it will pull on Earth. Here's the calm answer. Gravity depends on mass and distance. A mountain-sized rock far away has less pull on you than a bus parked down the street. 3.1 ATLAS is small by planet standards, and it spends its time far from us. Its gravity is tiny compared to the moons or even to large asteroids we track. The moon raises our tides every day. This traveler can't. The planets won't wobble because of it. Satellite orbits won't shift. Your coffee will taste the same. Let's put a picture on it. If the Earth were a beach ball, the moon would be a tennis ball about 24 feet away. A typical interstellar object is more like a pea thrown past the field at highway speed. Could you feel the pea's gravity while it rushes by? No, the pea doesn't tug. The beach ball, the tennis ball doesn't care. That's how far the pull myth is from the numbers. The only time a small body's gravity matters to us is in a direct, close pass, and that's the thing surveys are built to rule in or out early. In this case, they ruled it out. So, what's the real worst case with gravity? There isn't one. Gravity is the one box you can check as no problem and move on. The energy that could ever matter would come from a collision, not a pull, and that's the next thought experiment. We'll handle slowly and clearly. Chapter 4, the impact thought experiment short summary. Walk through a hypothetical impact to explain energy, size, and probabilities and why the odds are near zero. Now we'll carefully touch the scenario. People worry about most an impact. Not because it's likely, here it isn't, but because understanding the numbers will quiet the part of your brain that keeps asking, what if? Impact risk comes down to three things: size, speed, and where it hits. A house-sized rock burns up or explodes high in the air. You might hear a boom and see a bright streak. A bus to building-sized rock can produce a local airburst, like Chelyabinsk in 2013, windows shattered. Injuries from glass, but no global effects. A city killer would be larger, and those are rare. Surveys find most of the big ones, and none of those are on course to hit Earth in the foreseeable future. For 3 IATLAS specifically, the geometry and speed make an Earth hit exceptionally unlikely. Think of straight lines on a huge basketball court. Our court is 1 billion times larger, and the ball we worry about is tiny. If, against all probability, a fragment from an interstellar object did aim for Earth, you would see the news show up in hours, 2 days, on the Minor Planets Center and JPL pages. This isn't a no one is looking story. The whole world looks. You would see new observations, shrinking uncertainties, and a path that points exactly where and when. That hasn't happened, and the open path makes it even less likely. But let's stay with the thought experiment to understand energy. Kinetic energy is 1 half mass times speed squared. Speed matters a lot. Interstellar objects are fast. That means even a small piece can carry a big punch compared to a slow rock. That punch, however, has to land. And landing is rare. If it did, effects would vary. Over the ocean, you'd see a splash and possibly a local or regional wave if the rock were big enough. Over land, a mid-air burst would be most likely and mostly a local event. Global climate effects, the kind people fear, need big bodies, miles across, and those are found decades to centuries in advance. 3.1 ATLAS is not that. What's the real worst case here? For this visitor, a hypothetical fragment large enough to cause a local event, but detected in time, to warn people to stay away from windows and avoid travel in the affected area. That's not a doomsday. It's an emergency alert you can understand and respond to. And again, the odds today are extremely low. Knowing that, you can let the movie scene go and keep the part that helps. Pay attention to real pages, not rumors, and trust that a true hazard would be obvious in the data first. When people hear tail, they imagine a thick cloud sweeping across space like smoke from a factory. A comet's tail is not like that. It is incredibly thin, so thin that if you stood inside it, you wouldn't know. There are two kinds of tails. One is dust, tiny grains pushed back by sunlight. The other is ion, gas made of charged particles pushed by the solar wind. Both look dramatic in photos because long exposures collect faint light over time. But in terms of mass per volume, a tail is the thinnest fog you can imagine. So could Earth pass through a dust tail? Yes, in principle. We already pass through streams left by normal comets. That's what meteor showers are, the Perseids, Leonids. When our planet crosses a trail of older dust, some grains fall into our atmosphere and burn as meteors. They are beautiful. They are also small sand grain, small. They burn up 50 to 80 miles above us. You might see a brief uptick in meteors for a night or two. That's the worst for people on the ground. A nicer sky show. How about the ion tails, the glowing gas? That is even less of a concern. The ion tail is made of extremely thin, excited gas being pushed by the solar wind. If Earth intersected part of it, our magnetic field and upper atmosphere would shrug it off. You would not breathe it. It would not poison the air. It might, at most, tweak sensors that listen for charged particles, and even then only a little. The ion tail is more like a light breeze at the edge of space than a storm. A related question is, could dust from 3I Atlas add to a temporary debris environment near Earth? The answer depends on geometry and timing. Most interstellar travelers are fast and do not leave dense, long-lived streams near us. Even if a faint trail crossed Earth's path months or years later, the effect would be like a light meteor shower, far milder than the big annual showers we already enjoy and safely manage. So, what's the true worst case in this tail scenario? For people, nothing harmful. For power systems and radio, nothing unusual. For satellite operators, a small predicted bump in micrometeoroid flux for a few hours, handled with standard procedures. We'll talk about those next. That's it. The bright pictures trick the eye. The numbers calm the mind. There is one more useful picture to keep. Density versus time. Dust near the comet head is denser. Far behind, it spreads out and thins. Earth would cross the thin part if it crosses anything at all. That is why meteor showers are usually gentle, and why even the stronger ones are well within what we live with every year. The tail is a signpost, not a threat. If there is a place where worst case gets practical, it's not on the ground, it's in orbit. Satellites and spacecraft can feel small dust hits as tiny pings. But this is not new. Engineers designed for it. They use Whipple shields, thin bumpers that turn a small grain into a harmless cloud before it reaches the main wall. They point sensitive surfaces, like big solar panels, away from the expected radiant during a strong shower. They delay non-critical maneuvers for a night. They bias reaction wheels and keep instruments in safe modes if needed. It's all routine, learned from decades of living under showers that are much more predictable and sometimes stronger than anything an interstellar traveler would leave behind. Let's break it into simple pieces. There are three main orbits where we care: low Earth orbit LEO, medium MEOW, and geostationary GEO. LEO is crowded space stations, Earth imaging satellites, many communications birds. These vehicles already live with a steady drizzle of micrometeoroids and orbital debris. Operators plan for upticks during big showers like the Leonids. They adjust attitudes and limit thruster burns to reduce risk. A tiny increase from a faint interstellar stream, if it happened at all, would be less than the spikes we've already handled. The worst here is a small chance of superficial pitting, a sensor glitch, or a lost pixel in a camera not system failure. Meow holds navigation satellites. Geo holds many TV and data satellites. Both are farther out and face lower flux overall. During showers, the risk profile changes little. Operators use conservative modes, and any transient hits usually show up as brief noise, not damage. Spacecraft engineers also use redundant systems, error correction in computers, and shielding around critical boxes. The sky is not empty, so we build with that in mind. What about probes around other worlds? Mars orbiters, for example, already have micrometeoroid risk baked into their operations. If a predicted meteor outburst for Mars looked likely, teams could orient spacecraft, suspend delicate imaging, and wait a few hours. Rovers on the surface are highly unlikely to be affected. Their vulnerable parts are small, and the sky over Mars is vast and thin. A single bright meteor streak is more likely than direct trouble. The practical notes round this out. First, the biggest risk to satellites is still human-made debris in solar storms, not comet dust. Solar storms can pump energy into the upper atmosphere, which puffs up and increases drag on LEO satellites. That is a well-known effect with well-known mitigations. Second, industry and agencies share alerts. When one group sees an uptick, others get the message and adapt. We run space like a team sport. It's quiet on the outside, but inside, playbooks are real. So what's the genuine worst case for satellites tied to 3i Atlas? A short operational pause for a subset of vehicles, while a modest predicted bump in dust passes by, and even that is a stretch, given the speed and geometry of interstellar visitors. No satellites falling from the sky, no worldwide blackout, just standard spacekeeping, the way airlines reroute around thunderstorms, without anyone on board noticing more than a different view out the window. People often ask, okay, maybe Earth is fine, but what about Mars? It's a fair question, and it's useful because it shows how local these effects are. If 3i Atlas or fragments passed very close to Mars, the worst case would look like a small, brief meteor storm in the Martian sky, not a planet-wide disaster. Think of the 2014 comet siding spring event. It flew close by Mars. Orbiters took observations and then oriented themselves to reduce risk. The planet saw a shower of meteors in the upper atmosphere. Some chemical tracers showed up, and then it was over. No deeper shock to the planet, no long-term damage. Let's walk through the knobs Mars teams could turn. Mars Reconnaissance Orbiter. Mr. O. Maven, ESAS, Trace Gas Orbiter, TGO, and others can orient to reduce cross-section and pause sensitive modes. They can use their versions of storm posture, a calm step that protects instruments without risk to the spacecraft. Mars Surface Assets rovers, like Curiosity and Perseverance, are sturdy machines. They're built to handle dust, wind, and temperature swings. A meteor burning high overhead is mostly a light show. The chance of a tiny fragment making it down near a rover is astronomically small, like worrying. about a single grain of sand in a storm finding the one pinhead in a stadium. Could a NearMars seed new meteorites on the surface? Possibly, in the same way normal meteoroids do all the time. That's a science we're new stones to study, maybe decades from now, if anyone goes to fetch them. Could Mars orbiters or landers see glows, ripples, or upper atmosphere chemistry briefly change? Yes, MAVEN, which studies Mars' atmosphere and solar wind interaction, might record a short-lived increase in certain ions or a faint, high glow like a gentle fingerprint that fades. What about Phobos and Deimos, Mars' small moons? Their surfaces are already covered in dusty regolith. A tiny uptick in micrometeoroid hits would be just another tick in the long history of slow sandblasting they live with. No structural threat, no big effect. How does any of this reach Earth? It doesn't. Space is not a pool where waves propagate from one event to splash a faraway shore. Effects are local. Mars is its own bubble with its own rules. The same is true for other neighbors. If a pass occurred near Venus, we would not feel it here. If a far-out arc brought 3I, Atlas, near Jupiter, the story would be different for Jupiter's moons, an aurora still local. Still not ours. The positive side is that these local events are gifts to science. They let us test models for dust, tail, physics, plasma waves, and atmospheric responses under conditions we rarely catch. That means better forecasts next time, and stronger playbooks for spacecraft that might, one day, want to fly deliberately through a tail to sniff it. The worst case at Mars is operational some hours in safe orientation. The best case is knowledge, and that's the pattern you'll notice in every chapter. For people on Earth, worst cases are either not relevant or handled quietly by the folks whose job it is, while the best cases are we learn something new about how the sky works. If you've stayed with me this far, you may feel a small shift inside. The pictures in your head are less dramatic, and the paths to answers are clearer. That's the whole point. Calm is not denial. Calm is what happens when you replace a fog of what if with a few clean here's how. In the next chapters, we'll keep walking through Breakup and Fragments, the radiation rumor, and why panic is often the real worst case for people. And we'll keep that same easy pace because the sky is patient, and so are we. Breakups sound dramatic because we picture a solid thing turning into shrapnel. Comets and small interstellar visitors are different. They can be fragile, like loosely bound rubble or icy foam. Heat, spin, or a close pass by a planet can pull them apart. We have watched these many times. Comet Shoemaker-Levy 9 broke into a string of pearls under Jupiter's tides in 1992 and later fell into Jupiter, not Earth. Comet 73P, Schwarzmann-Walkman 3 shed dozens of pieces along its orbit in 2006. Each time, the fragments continued more or less along the original path, spread out by small differences in speed. If 3 IATLAS fractured, the center of mass would still follow the same kind of open, interstellar track. Smaller pieces would drift ahead or lag behind. The overall cloud would become longer and thinner with time. For Earth, this usually lowers risk. One large body turning into many small ones spreads energy out and increases the chance everything burns up high in the atmosphere if anything ever intersects our path at all. The air is very good at turning small stones into streaks of light. There are 3 common ways a breakup can happen. The first is thermal stress. Parts of the body heat and cool unevenly and crack. The second is spin-up. Sunlight gently torques. A misshapen object, the Yorp effect, and if it spins too fast, weak bonds fail. The third is outgassing. Jets push from within and pry seems loose. None of these add new energy. They redistribute it. Picture a slow-moving snowball shedding crumbs. The crumbs do not become bullets. They are crumbs moving at similar speeds. Only now they show up as more dots for telescopes to follow. How would we know a breakup occurred? The brightness curve would flicker or plateau oddly, then recover as multiple pieces dominate the light. High-resolution images might begin to show more than one nucleus. Surveys would report multiple detections along a track that used to have one. The Minor Planet Center would list them. JPL fits would shift from one solution to several related ones. You would see this in days not as a rumor, but as a run of small, clear lines that say observed here, observed again, observed again. That is how you can tell a real split from a shaky video. What would be the true worst case with fragments for Earth? A piece large enough to make a local airburst, discovered late. That scenario is still very unlikely because survey telescopes scan the sky nightly, and a piece big enough to matter is bright enough to see. If such a piece existed, you wouldn't hear speculation first. You would see fresh observations, rapid follow-ups, and official notices. Local authorities would get briefings. Airlines would shift routes if needed. The path from detection to decision is well rehearsed. The odds you would wake up with no warning to a large, unseen fragment are tiny. For satellites, a breakup can mean a narrow window of slightly higher micrometeoroid flux if Earth crosses a faint train later. Operators already manage those bumps during normal meteor showers and would treat this the same way. Change attitudes. Pause delicate modes. Wait a few hours. In practice, the sky turns a supposed worst into a routine plan. Protect the vulnerable, then go back to work. The word radiation is heavy, so let's set it down and pick it up carefully. In everyday space talk, radiation usually means energetic particles from the sun's solar energetic particles, or high-energy cosmic rays that come from our galaxy. Sometimes we also mean Z rays or gamma rays from extreme events like solar flares or distant bursts. None of that is made by a small comet or interstellar pebble. A body like 3I Atlas reflects sunlight, emits faint infrared heat, and, if it is active, produces an ion tailfin, excited gas pushed by the solar wind. That gas is too thin to matter at Earth, and is not the same thing as radioactivity. Why do rumors about beams or blinks appear? Usually because of how instruments listen. Detectors count particles in time slices. If a solar storm arrives in pulses, and your detector samples with a certain rhythm, you can make a plot that looks like a code when you line up bins wrong or subtract a rolling average that is too short. Another common cause is background subtraction around the object. If you subtract the sky with a narrow box that includes a gradient or scattered light, you can carve smooth changes into stripes. The cure is to compare raw counts and use a second instrument. If two independent detectors with different sampling see the same timing, then you ask more questions. Most of the time, the pattern washes out under a different bin size or a different sensor. Could a comet carry radioactive materials that irradiate space? The answer is no in any useful sense. The tiny amounts of natural radioisotopes in rocks are insignificant at astronomical distances. You receive more dose on a long airplane flight than from a comet passing by the moon. The specific radiation environment that matters for astronauts and satellites is set by the sun's cycle. Flares, coronal mass ejections, and the steady drizzle of cosmic rays. Space weather forecasters at NOAA, WPC, ESA, and other agencies monitor those and post alerts. They are not watching comets for radiation hazards, because comets do not make them. What would be a true warning sign? A solar event measured by many spacecraft, a spike in proton flux, a ENS ray flare classed by GOES satellites, ACME reported in coronagraph images. Those are the events that can trigger radio blackouts, cause auroras, and sometimes induce currents in power grids at high latitudes. Even in those cases, you hear from trusted sources first, not a single plot on social media. If you ever see radiation from 3I ATLAS, translate it to "let's check if a solar storm was happening." Then open the space weather page and look at the official dashboard for people on the ground. Worst case from this rumor is worry. You do not need iodine tablets for a comet. You do not need to stay indoors. If there is a real solar storm on the way, official channels will say so, and their advice will be boring and practical. Satellite operators may take precautions. Airlines may reroute polar flights. Auroras could be strong tonight. That's all. The sky's dangers are old news to the people who guard against them every day. Comets are not on that list. Panic is sneaky because it feels like action. Your heart races. You read faster. You share. You do something. But panic rarely makes you safer. For sky stories, it makes you tired and less able to tell rumor from record. The good news is that panic has weak seams. A handful of simple habits pull it apart. The first habit is the 2-page check. Before you share anything, open the Minor Planet Center confirmation page and the JPL small body database. If a claim is real, it will grow on one or both of those pages within hours, 2 days. If you never see it there, that tells you something without any argument. For solar storm claims, swap those pages for NOAA SWPC's dashboard. Make those links easy to tap. The easier the link, the less your brain reaches for a screenshot instead. The second habit is the time cushion. When you see a dramatic post, say to yourself, "I will check again in 24 hours." That single sentence steals fuel from panic. It gives the world enough time to repeat or retract. It's amazing how many frightening ideas do not survive a sunset and a sunrise. While you wait, do not feed the algorithm that is yelling at you. Close the app. Open a real page. Make tea. Go outside and look up. The sky does not care how loud someone was this afternoon. The third habit is the 3 questions. Who is the source? Where is the data? Does a second group match it? If a clip cannot answer those, it is not proof. It is a prompt for you to be kind to yourself and wait. If a scientist posts a cautious note with a product ID or a link to a raw image, treat it as a doorbell, not a verdict. If a stranger posts a cropped image with no time, no coordinates, and a caption in all caps, treat it as a request to protect your sleep. The fourth habit is word choice. Flag words that make your pulse jump and move them to the back of your mind. Impossible, weapon, secret, meltdown, these are not data. Trades them for the quiet words that carry weight. Eccentricity, inclination, non-gravitational term, light curve, triangulation. You don't need to be a professional to use those. You only need to know they are the words that grew up in rooms where people argue with plots, not with each other. The fifth habit is to remember the scale of real risk. On an average day, weather on Earth is more dangerous to you than weather in space. storms, heat, ice, that is the world you walk in. If a comet were ever a real threat, you would not learn it from a rumor. You would see coordinated posts from agencies you already know, echoed by meteorologists and emergency managers in your state. The internet likes to flip that order because it rewards being first. Your life rewards being right. Creators, journalists, and curators have a role in this too. The messages that go the farthest often come from people who have learned to be loud without being cruel. If you make things for others to watch, try a small rule that helps more than it seems. Never publish a sky claim without one link to a primary page. If you do that, you will make fewer frantic videos and more useful ones. Your viewers will sleep better because you gave them a path back to the source without asking them to trust your mood. The last thought in this chapter is about your body. Panic lives in the chest. You can quiet it in the body even as your mind gathers facts. So, while you wait for numbers, do one small physical thing. Breathe slowly for 1 minute. Or step outside and feel the air for 30 seconds. Or put your phone down and wash your hands with cool water. These tiny acts break the loop that keeps the fear part of your brain driving. When you pick the phone up again, you will be better at seeing what's true. If you have felt fear during this story, that is human. These questions touch the oldest part of us, the part that wants to protect our family. The gift you can give that part is a short list of habits. 2 pages. 24 hours. 3 questions. Better words. Local risk first. 1 minute to breathe. Put those on a note. Put the note next to your favorite link. That is how you build a bridge you can walk across the next time the sky gets loud. If worst case ever tried to visit, you wouldn't meet it alone. Planetary defense is a real, daily job split across many teams, and most of the work happens before anything becomes scary. Think of it as 3 layers. Find, understand, and if needed, nudge. The find layer is wide and constant. Olski surveys scan the heavens every clear night. Panestia Raz in Hawaii, Catalina and MT, Lemon in Arizona. Atlas across multiple sites, the Zwicky Transient Facility in California, and, soon, the Rubin Observatory in Chile. They take short exposures, subtract yesterday's sky from tonight's, and flag anything that moved. Those flags tracklets go to the Minor Planet Center, where they become lines on the Near-Earth Object Confirmation page. That page is the public waiting room. The world's telescopes can pick targets from it and add positions, shrinking errors with each new dot on the sky. The understand layer starts as soon as 2 or 3 nights of data exist. Orbit fitters at JPL and other centers compute a best fit path with uncertainties. The JPL Small Body Database hosts the orbit page most people check. For potential hazards, the Sentry system runs millions of virtual futures. If the rock's orbit was a little this way or that, would any path hit Earth in the next century? The results are posted in public as risk tables, with familiar scales. Torino color-coded from 0 to 10, and Palermo, a logarithmic score used by professionals. Most new objects sit on Torino 0 or 1, and then drop to 0 as more dots arrive. That is the normal rhythm. Scores go down, not up, because uncertainty shrinks and the cloud of future paths collapses away from us. The nudge layer is the small toolbox we open only if needed and only with time to spare. The kinetic impactor, the push with a fast shove, is no longer theory. NASA's DART mission slammed into the moonlet. Dimorphos in 2022 and shortened its orbit around Didymos by minutes. Exactly the kind of measurable tweak we would want in a real case. A gravity tractor, heavy spacecraft that loiters nearby and tugs gently for years hasn't been flown as a deflection demo, but the physics is simple and the engineering is mature. There are louder tools on paper like standoff nuclear options to vaporize a surface patch and use the blow-off as thrust. But planetary defense is built around long lead times and quiet solutions. Small nudges early are better than big ones late. The whole job is timing. There is also a drill culture. NASA, ESA, FEMA, and partners run tabletop exercises where a fictional rock shows up with a tricky orbit and a date. Teams practice who calls whom, which pages update when, how uncertainty shrinks day by day, and when to hand the baton from astronomers to emergency managers. Those drills have already discovered little gaps, and those gaps were fixed. It is not glamorous work, but it is the kind that matters most on a day you hope never comes. What would you see if a real risk ever developed? First, you'd see the MPC page fill with observations from all over. Then you'd see a JPL orbit page with shrinking uncertainties, and an item appear on Sentry with a non-zero Torino score. You'd see press briefings with specific dates and ranges, not vibes. You'd see your local meteorologists and emergency officials share the same numbers the astronomers are using. That sequence happens in days to weeks, not minutes sand. It gives time to breathe and act. For 3i, Atlas, none of that sequence is happening, and the open, interstellar path makes the nudge layer unnecessary. Still, it helps to know the toolbox exists and has already passed a flight test. Comets get dramatic near the sun. Heat climbs. Aces sublimate into gas. Dust lifts. Tails bloom. That's when cameras catch them at their best, and sometimes when they break. This is the sky's gentle stress test. Sun grazers discovered in Soho coronagraph images often disintegrate completely in the hot light of the sun and never come back out. Others survive but lose mass, shed fragments, or fade after a brief show. It's a cycle we've watched for decades with Soho, stereo, and ground-based coronagraphs. Perihelion is danger for the object, not for Earth. What does perihelion risk look like for us? Mostly, it doesn't. The distance from the sun, our closest approach, and the geometry of the orbit define where the tail points. Ion tails are swept straight by the solar wind. Dust tails curve gently with the object's path. Unless Earth is directly lined up to cross. A fresh dust ribbon, later, and that alignment is rare for fast interstellar visitors. We see only a pretty sky and then a fade. Even if a thin stream crossed our path months later. The worst for people would be a soft meteor shower. The interesting physics lives in how the object responds. If it has low tensile strength, venting can widen old cracks. If it spins, period shortens under uneven sunlight, the yaw perfect, centrifugal forces can open seams. The surface bakes and flakes. None of this adds new energy to threaten us. It only changes the way the visitor leaves, whole, chipped, or as a chain of pearls that will spread into a longer, thinner string. The center of mass still walks the same open road out of the solar system. Perihelion is also when you see the best science photos. Coronagraphs hide the sun's bright disk, revealing faint comets diving into the glare with long, living tails. Solar orbiter and ground scopes sometimes catch ripples racing down those tails, waves driven by the changing solar wind. Those ripples can look too neat to be natural in a single frame. When you watch them with wind data next to you, they read like music synced to a metronome. Risk does not live in those waves. Knowledge does. A small body's light curve the way its brightness rises and falls tells you its spin. If the curve is steady and repeats, the object is turning like a clock. If the curve is messy or shows multiple periods, it might be tumbling, rotating around more than one axis, or changing in real time as jets switch on and off. From that beat, you can predict a lot. When one face turns sunward, you might expect a small puff of gas. That puff is a tiny rocket. Over hours, tiny rockets add up to a track you can measure from Earth. Astronomers fold those puffs into orbits with 3 small non-gravitational terms, often labeled a 1, a 2, and a 3. You can think of a 1 as a push, generally away from or toward the Sun. A 2 as along the path speeding up or slowing down a hair, and a 3 as sideways out of the orbital plane. For most active bodies, a 1 is the main actor. A classic sign that you're seeing nature, not control, is when the size of a 1 fades with the square of distance, sunlight weakens with distance, and its direction lags a bit behind high noon on the object's surface. Heat takes time to build and to cool. Could a small body maneuver in a way that matters to Earth? In practice, no. The energy needed to change a fly-through miss into a hit is huge compared to the energy a weak jet can supply in a few days. Real delta v the change in speed from rockets and gravity assists, and even then it takes careful planning. A comet's breath cannot turn a corner to chase a planet. What it can do is shift timing by minutes or hours and distance by thousands of miles, plenty to matter to a telescope's schedule. Not enough to invent a threat. The other piece is stability. Teams on different continents fit the same dot train and compare results. If one group says the object needed a sideways push and another says it didn't, the cure is time. More nights, better geometry, and sometimes a different choice of how to weight noisy measurements. Real drifts that come from sunlight survive those checks. Imagined turns fall apart. For 3I Atlas, any small drift measured by teams would be part of the natural story, interesting to model, irrelevant to our safety, and one more reason to love how careful numbers deflate loud ideas. There is a quiet worst case in this chapter, but it's the one that helps spin up to break up. If sunlight spins a fragile body too fast, it can split. That moves us straight back to Chapter 8's comfort. Smaller pieces, thinner streams, lower risk, more dots to watch for science. Nature's worst case for the object is still a soft case for us. Let's walk the question. People ask in whispers, what if something hit the ocean? We'll do it slowly, with real numbers, because understanding is the best sleeping pill for worry. Pick 3 sizes to see how scale changes outcomes. A 10-meter rock about a house, a 50 to 60-meter rock. Chelyabinsk was approximately 20 meters. Tunguska was approximately 50 to 60, and a 140-meter rock, the size where survey law focuses, hard Congress, chose 140 meters as a key threshold. Then keep in mind, interstellar objects like 3I-ATLAS are on open paths and extremely unlikely to line up with Earth at all. This is a model, not a forecast. A 10-meter object breaks up high in the air. Over water, you'd see a flash and a small pressure wave aloft. No tsunami. Energy departs in the sky. A 50 to 60-meter object can produce an airburst lower down. Over land, that can knock down forests regionally Tunguska. Over water, the blast couples to the surface and may raise a local wave, but not a bossing crossing wall. Most energy still spends itself in the atmosphere. Broken windows, injuries near shore if the burst is very low and very near land. Far-field coastlines see little or nothing. A 140-meter object is serious. Over land, it could destroy a city if it hit directly. Over ocean, it would punch a transient cavity and launch waves. Here's where myth and math part company. Movies show a single skyscraper wave racing across an ocean unchanged. Real water spreads energy out and breaks it into wave trains that disperse. Near the impact, wave heights can be very large, dangerous to ships and coasts within tens to a few hundred kilometers, depending on depth. As waves travel, they lose height, sort by period, and feel the shape of the seabed. By the time they cross a basin, they're smaller and longer, more like fast tides than falling walls. That still dangerous close to shore water can run far inland in low-lying areas, but it isn't uniform doom for all coasts. Modern studies use high-resolution bathymetry, seafloor maps, and hydrodynamic codes to model these waves. The results agree on the big idea. The near field is where the greatest danger lives. Far-field impacts are patchy and much lower than people think from posters. Also, warning works. If an impact were predicted hours, 2 days ahead, the normal case for something this large, tsunami warning centers could use seismic, ocean bottom pressure sensors, satellite altimetry, and coastal gauges to confirm and issue evacuation alerts for specific shorelines. Evacuation routes exist in many places. Sirens work. People practice them. Worst case in the far field is not no chance. Now fold in the key point 43I Atlas probability. A direct strike by a fragment large enough to matter is already extremely unlikely in this case. The visitor is on an open path and spends almost no time in Earth's hitting box. Even if you ignored that and asked what if, the chain still has rungs for safety. Early detection, public risk pages, clear windows for rerouting ships and planes, and hours for coastal civil defense to act. The world handles hurricanes that are orders of magnitude messier than this scenario every year. An impact is simpler. A date, a place, an energy. You can plan for that. The biggest practical comfort is the long lead. Discovery record for truly large bodies, kilometers. The surveys have found the overwhelming majority. None are on a collision course with Earth in the foreseeable future. That's why professionals sleep well at night. And it's why you can, too, even while you enjoy the calm thrill of asking hard questions and answering them with numbers instead of nerves. When people ask about a hit on land, what they usually mean is an airburst. Most stony meteoroids are not solid iron. They're mixed, cracked, or simply not strong enough to punch all the way down at cosmic speed. As the atmosphere thickens, pressure builds on the front face. The rock heats, flexes, and fails. It breaks apart at high altitude and releases its energy into the air as a flash and a shockwave. That is what happened over Chelyabinsk, Russia, in 2013. The object was about 17 to 20 meters, across roughly the size of a small house. It exploded around 18 to 23 kilometers up. The flash was bright enough to throw sharp shadows. The shockwave circled the globe more than once. More than 1,000 people went to the hospital, mostly for cuts from blown-out windows. Buildings were not flattened. The power grid did not fail. Airliners did not fall. The event was dramatic on video and local in effect. A larger airburst happened in 1908 over Tunguska, Siberia. That object is thought to have been something like 50 to 60 meters across. It exploded lower than Chelyabinsk and over forest. Trees were knocked down across a wide area. There were no modern cities nearby. Even at that size, the event was regional, not global. The biggest lesson from both cases is practical. The danger to people is mostly glass. When you see a bright flash, your first instinct is to run to the window and look out. Minutes later, a shockwave arrives and shatters the glass into your face. The simple rule is the opposite. Do not stand at the window. Turn away, step back, and wait for the boom to pass. It's the same duck and cover habit that protects you in a thunderstorm when lightning hits close and thunder shakes the house a few seconds later. What sets the scale of an airburst? Two numbers, size and speed. Speed is squared in the energy equation, so it matters a lot. Interstellar objects are fast, but size matters more for harm. A 5 to 10 meter rock becomes a fireball high in the sky. A beautiful streak, a loud boom, maybe a sonic crack that rattles things. A 20-meter rock like Chelyabinsk breaks lower and throws a stronger wave. A 50 to 60-meter rock like Tunguska can knock down structures near ground zero if the burst is very low, and flatten trees out to tens of kilometers across. Above that, at 100 to 140 meters, you are in the range where an intact body could reach the ground and make a crater, especially if it is iron. Those sizes are rare, and surveys are good at finding them. That is exactly why global risk tables focus on 140 meters and up. What would warning look like in a modern airburst? We already have it in layers. Space-based sensors, optical and infrared, often detect the incoming glow before breakup and record the flash. Infrasound stations, part of worldwide monitoring networks, catch the low-frequency wave and triangulate the blast altitude and energy within minutes to hours. Social media fills with clips, yes, but emergency managers and meteorologists also start to share calm notes. A meteor exploded over region. Expect a loud boom. Stay away from windows. That happened after Chelyabinsk. It will happen faster next time because the drill is better known. What about fire or chemical risk? Most airbursts do not start ground fires unless fragments reach dry brush during a windy day. Even then, you are talking about normal wildfire response, not a special class of hazard. Air is not poisoned by an airburst. You would not need to shelter for fumes. And if small fragments survive, they hide in the snow or soil, tiny stones that scientists may hunt a day later with magnets, bags, and gloves. Is there an airburst? Worst case, that would touch many cities, not from a single small body. Harm scales with distance. Pressure waves weaken as they spread. You might see broken windows across part of a large metro area if the burst is low and nearby. You would not see continent-wide damage. You would not see global climate effects. Those belong to impacts by bodies a mile wide or more, and those bodies are found decades in advance. 31ATLAS is not in that class. And interstellar objects spend too little time near Earth to sneak up unseen. The habit that matters most in an airburst is simple and easy to remember. If the sky flashes bright, step back from glass. If you're outside, don't stare straight up. Put your back to a wall or a tree and count a few seconds. The boom will pass. When it has, you can go back to watching the sky. Turn that into muscle memory now, and you'll never need a narrator to tell you again in the moment. You'll just do it, and you'll be fine. It helps to rehearse the sequence once, so you can recognize it without anyone selling it to you. Step 1. A candidate appears on the minor planet centers near Earth. Object confirmation page. That's the signal for watch this. In the next 6 to 24 hours, other observatories add positions. The page fills with new lines from different codes, small telescopes, large telescopes, sometimes amateurs with excellent gear. If it's cloudy in one place, another site picks up the slack. With 2 or 3 nights of data, step 2 happens. An orbit appears in the JPL small body database. Uncertainties are big at first, then shrink as more dots arrive. If the object is not interstellar, its eccentricity settles below 1. If it is interstellar, eccentricity remains above 1 with smaller and smaller error bars. Either way, you watch the numbers stabilize. If any futures cross Earth's path in the next century, a step 3 appears. The object shows up on JPL's Sentry risk page with Torino and Palermo scores. Most entries start at Torino 0 and stay there. If anything non-zero shows, you'll see a date range and a probability that changes as data get better. The usual direction is down, no risk, because uncertainty collapses away from us as details sharpen. If a small residual risk persists, you'll see clear language in press briefings that matches the tables. No vibes, no drama, dates and ranges. Step 4 is who calls whom. If a specific region might be affected years, months, or even days from now. The chain goes from astronomers to national agencies to local emergency managers and meteorologists. These are people you already trust for weather and wildfire. They'll use the same tone they use every season. Here's the timeline. Here's the path window. Here's who might need to move when. Here's what we'll know tomorrow. If we are years out, you'll hear about mission options. We can nudge this. If we are days out with a small airburst expected, you'll hear about sheltering indoors and staying away from windows. In none of these paths is there a need for a secret hot take from an influencer. The real signal is boring on purpose. A true threat also brings many eyes. You'll see consistent plots from different universities. You'll see public dashboards updates. You'll see software like JPL Horizons give consistent positions for telescopes to aim. You'll see your local news share the same link the astronomers use. When the truth is real, it repeats. It does not hide in a single video. The first place it becomes visible is not the loudest feed. It's the simplest page. What would you not see? It's coming tomorrow and no one knows. That cannot happen with an object large enough to hurt many people. A kilometer-sized rock is found decades to centuries early. A Tunguska object is seen days to weeks out unless it comes from a direction where the sun hides it. And even then, infrasound, satellites, and radar pick it up minutes to hours before the boom. And again, 3IATLAS is not in the geometry to do any of this. The exercise here is to store the template, MPC lines, JPL orbit with uncertainties, shrinking, Sentry risk, entry or not, then local guidance. If those steps aren't present, you can drop your shoulders and move on. The internet is good at finding your buttons and pushing them. For sky stories, the buttons are words like secret, impossible, weapon, and meltdown. The fix is not to swear off the internet. It's to spot red flags in a second and step around them. The biggest flag is a screenshot with no time, no location, and no path back to a primary page. If you can't click through to a raw image, an MPC line, or a JPL orbit, you're not looking at a measurement, you're looking at an advertisement for your attention. Another flag is a single detection that never gets a friend. Real objects get second, third, and 10th detections within hours to days. If a claim about a fragment, a turn, or a blink never gets a second eye, it belongs in a folder labeled curiosity, not confirmation. A related flag is a background that doesn't match the claimed time and place. Wrong stars, wrong sun, angle, wrong horizon. You can check that with a free Sky app in under a minute. If the scene can't exist, the claim can't live. A third flag is edits that hide the instrument. If color, contrast, and cropping are heavy, ask for the raw frame or the product ID. Scientists who share early usually include those. If someone cannot or will not, that's your sign to protect your time. A fourth flag is a strong claim attached to a weak pattern. It lines up with Stonehenge and a Bible verse and this orbit line. That's not how orbits work. Orbits live in math and in the sky, not in calendar tricks. There are softer tells that will save you hours, too. Any sentence that starts with NASA knows but won't tell you can be translated to the speaker has not checked the MPC. Any video that uses the same 3 frames rotated, zoomed, and looped is trading on your nervous system, not on data. Any thread that refuses second opinions is not science. It is theater. You have permission to walk out. What do you do with a gray claim, something that looks interesting but not solid? Give it 24 hours. Bookmark the MPC page and the raw archive you think it belongs to. When you come back, you will know whether it grew or dried up. That habit will turn you into the calm person in your group who says, "Let's check the page before we spread that." You don't need a degree for that. You need a pause and 2 links. Worst case fades fast when you see how much good sits inside these events. A single interstellar object is a sample from another solar system delivered to our doorstep at high speed. We don't get to pick it up with Tongzet, but we can read it with light. Spectroscopy tells us which gases are present if it's active CN, C2, CO. CO2 are common in comets, and how the surface reflects light if it isn't. A red slope can mean space-weathered organics. A neutral slope can hint at metallic or fresh surfaces. Polarimetry, the way light's polarization changes after reflection, adds another clue, especially for dust size and texture. Dust itself is a treasure. When a tail passes in front of stars, we can study how the light dims and scatters, which tells us about grain sizes and shapes. That information feeds straight into models for planet formation because planets start from dust. If 3I-ATLAs carries grains different from what we see in local comets, that suggests its home system grew under different conditions, hotter, colder, richer in carbon, or poor in water. Each of those threads tightens our picture of how common, Earth-like worlds might be. The ion tail is a free probe of the solar wind. Ripples and kinks map changes in speed and magnetic field that are otherwise hard to catch in 3 dimensions. Putting tail images next to solar wind data from Spacecraft lets us test how well our space weather models work. Better models mean better forecasts for the real radiation that matters to astronauts and satellites. Solar storms, 12-world triangulation, Earth and Mars makes you faster at everything. Range and speed become facts. Orbits clamp down. Spin periods can be measured from 2 angles. The trick then becomes routine, and routine is the opposite of panic. The next time a visitor shows up, the radios will be ready, the commands will be rehearsed, and the data flow will feel like a drill we enjoy instead of a scramble we regret. Planetary defense training also gets a lift. Even when there's no risk, Teams practice the handoff from detection to characterization to what-if modeling. Tabletop exercises get updated with fresh lessons. Software that once needed a person to click through steps becomes a script that runs in minutes. A mission like DART moves from "we did that once" to "we are ready to do that again, for real, if the tables ask for it." The public side gets better. 2. Press kits improve, dashboards get clearer, and more people learn to use the primary pages. There's a social science win hiding here as well. Each time the sky gets loud, more of us learn the small habits that make the next time easier. The 2-page check, the 2 4-hour wait, the 3 questions, the calm words. Families build tiny rituals around looking up, going outside to watch a meteor shower, pointing a phone at the sky to find a planet, saving a link that goes straight to a real orbit page. That's culture. It is kinder than fear and stronger than rumor. Finally, there's the quiet statistical prize. With Oumuamua, Borisov, and now a third visitor, we can start to estimate how many interstellar objects sweep through the inner solar system every year, what sizes they tend to be, and how diverse they are. That number feeds into big questions. How often do planetary systems toss out debris? How many disks build comets rich in complex organics? How often could seeds of chemistry move between stars, not as a plan, but as a natural spillover in a busy galaxy? You don't need to believe in seeds to enjoy the math. The math is the seed. It grows new missions, new instruments, and new minds that will be the ones to answer the questions we can only whisper today. In the next section, we'll turn all of this into a small personal kit. How to watch without worry, what to pin, how to sleep when the feed is loud, and how to leave this topic tonight with shoulders lower than when you arrived. Then we'll close the circle gently, put worst case back in its box, and say goodnight to a sky that is big, quiet, and most nights very kind to everyone under it. Here's how to leave this topic tonight with clear guardrails and a lighter mind. Keep your world small and practical. Pin 2 pages you can check in under a minute. The minor planet centers, confirmation page, and the JPL small body database. If the sky ever delivers something that matters, those pages will change first. They are simple, quiet, and honest. If you're curious about space weather, add the NOAA Space Weather Dashboard as a third tab. That set is enough. You don't need a feed full of hot takes. You need 2 or 3 doors you can open when you want the truth, then close when you're done. Give yourself a little time cushion. When you see a dramatic post, tell yourself, "I'll check again in 24 hours." That single sentence is a soft shield. Real events repeat. Weak claims fade. While you wait, step outside for a minute and look up. You do not need to name the stars to feel the scale of them. Breathe in the cool air if you have it. Let your shoulders drop. Curiosity survives pauses. Panic does not. Borrow 3 easy questions each time something new pops up. Who is the source? Where is the data? Does a second group match it? If those are missing, set the claim down without anger and come back later. If a scientist shares a frame with a time and a product ID, treat it like a doorbell. We saw something, can others look? If someone shares a cropped, color-pushed image with no path back to a real page, that's not evidence. It's a test of your attention. You get to pass. Use calm words on purpose. Swap impossible weapon. And melt down for the words that actually move the ball. Eccentricity, inclination, non-gravitational drift, light curve, triangulation. You do not have to be an expert to say them. Each one points you to a small number that will either change in a clear direction or stop changing at all. When numbers settle, stories settle. Remember the scale of real risk. On any given day, weather on Earth matters more to you than weather in space. Storms, heat, ice, that is the world you live in. If a rock large enough to concern many people ever had a line to Earth, you would not learn it from a rumor. You would see matching messages from the same public pages the professionals use. Then from your local meteorologists and emergency managers. It would come as dates, windows, and ranges, not as a scary clip without context. It would give you time to prepare, or more likely, time to relax when the uncertainties shrank back to zero. Make a tiny kit you can use half asleep. Write these on a note and stick it near your screen. MPC gives JPL. To 4-hour wait. 3 questions. Calm words. Add one more line just for your body. Step back from glass if the sky flashes. That last habit is for the rare local airburst. It costs nothing to practice, and it pays off on the one day you might ever need it. The rest of the time, it's just a reminder that your safety lives in small actions, not in runaway thoughts. If you love space, give yourself a gentler way to enjoy it. Watch for meteor showers on a clear night and bring a blanket. Point a phone app at the sky and learn one planet and one bright star. That's enough to feel at home under the dome. If you have a pair of binoculars, look at the moon's edge and the craters near the Terminator. If a visitor, like 3IATLAS, is up and bright, step outside and try to spot the tail. You will feel the same old awe our grandparents felt on it. Now you'll carry it without the weight of unnecessary fear. As for 3I, Atlas, and the worst case, we've done what most people never do, walked straight toward the worry and answered it with physics. The open path means it is passing through, not staying. Gravity is not a threat. Tails are thin and beautiful, not harmful. Breakups spread energy out. Radiation stories are about the sun, not comets. Satellite teams have playbooks for dust, just as airlines have playbooks for storms. Planetary defense is real, routine, and built for early, quiet nudges should a different rock ever ask for it. And most of all, the places that matter, MPC, JPL, space weather dashboards, are in your pocket, ready to replace noise with clarity anytime you want. If this helped you breathe a little easier, keep this calm with you. Save the links. Share them with one person who loves space but hates panic. If you'd like more slow, clear guides like this made to help you think, and if you want to help you sleep tap, subscribe and leave a gentle note about where this clicked for you. Maybe it was the way tail ripples matched the solar wind. Maybe it was learning that worst case is mostly a planning word, not a prophecy. Either way, thank you for spending this hour in a quiet room with big ideas. Now dim the screen. Let the room grow still. The sky will keep moving at the same steady speed, and we'll be here for the next measured step, together, calmly, and in the open.